Hello.
Hi Tom, how are we doing?
Good afternoon.
Good stuff. I'm not too bad myself either. Nice one. So I'm literally just picking off from where we left off from,
Yeah.
if that's okay with you, because I thought you may probably not have had a chance to go through the questions. Is that okay, or do you have any pressing problems at present that you want to go to?
No pressing problems. I'm
Cool.
just ready to crack on.
Nice one. Okay, so let's have a go and start off with the lovely number 14. Yeah,
I'm just going to shut the window
Sorry?
because it's noisy outside. I'm just shutting the window because it's noisy outside. So
Okay, that's cool. That's all right. That's all right.
Neighbours decided to cut the lawn. Would current be constant throughout the whole time?
So this one, Tom, is a classic question. If you cast your memory back to when we looked at the maximum, it's actually a theorem, if you like. It's known as the maximum power theorem, max power theorem. And this is the one I highlighted, and I said it's often forgotten by students because the questions don't crop up often, but it's so useful. So when do we get maximum power delivered to a load? If I have a circuit like so, and it's got an internal resistance, what value of big R should I have if this cell is to dissipate maximum power to this load? What should the value of this big R be?
4 ohms.
Not quite.
I just thought because
R should be equal to the small r. So if the internal resistance is 2 ohms, maximum power will be delivered when the external load is also 2 ohms. Now, this is very similar to the classic encounter again, when you look at billiard balls, yeah? Maximum kinetic energy is transferred from one to another on collision because the masses are the same. So there's something about matching masses, matching resistances that leads to maximum power delivery.
So it's 8 then?
Correct, spot on. Okay, good. So please remember this theorem, it's super important. Okay, yeah. Right, number, not a problem. At least now, you heard it, but unless you kind of see it and have to encounter a problem, it's very difficult to remember these things when you've got other subjects on your mind as well. Right, number 15 for you then. Shall we go for 15?
Yeah. Can we do a little bit of photoelectric effect?
Oh yeah, sure. Not a problem.
I think I've forgotten a bit of it since I revised it.
Not a problem. I'll go through that with you. We've only got 5 questions in this, and we've got enough time to cover the thing.
Oh yeah, that's fine.
Okay, super.
I worked out the total resistance of the circuit is 7.5 ohms. I don't know if that's useful or not. Is it 2/3 volts?
You're spot on, Tom. Well done. Excellent, man. Excellent. Way to go. Very, very good. Super duper. Okay, let's have a go at 16 then, shall we? Now think about this one, Tom. This is not a very easy problem.
Okay.
So if you need to put in values, do put in values.
Can draw it out.
Yeah, correct. Worth thinking about this properly. Okay.
Are they connected to a battery?
Which one do you go for, Tom?
I said, are they connected to a battery? Are they connected to a battery?
Yes. Absolutely. They're connected to a power supply, correct?
Okay. Is it D? Is it D?
Not quite, Tom, on this one. I know it's really tricky. Not D though. Not D. Have you tried putting in some values? And they're equal,
No,
same one.
I just thought about resistors in parallel, and then I thought Y and Z would be unaffected, and then if
Okay,
the resistance in
what
parallel,
when
X would be greater.
the W is removed, what's going to happen to the amount of current in the circuit? Will it go up or down?
Stay the same.
No, it can't stay the same, because remember, if I have two resistors in parallel and each of these are 10 ohms,
Yeah.
what's the effective resistance of these two? What can I replace these two resistors with and still have the same resistance?
Is it a 5 ohm resistor?
Correct, 5 ohm. In other words, very simply, remember that when you have two resistors in parallel of equal resistance, they are effectively the same as one resistor with half the value of one resistor. Correct. So that's 5 ohms. So if I took out this 10 ohm resistor, what would happen to the current in my circuit? Imagine that's the path. So initially it's 5 ohms. I take out the 10 ohms. What's going to happen to my current?
Will it increase?
It will
Increase.
decrease, correct, because my resistance has gone up. So now use that rationale to try and work out what happens to power, remembering that power is I squared R. Are you okay with that?
Yeah.
Good, good man. Super duper.
All right. Is it B then? Is it B? Is it B?
Not quite. Let's go through this one together. Really quite diabolical, this one, I have to say. So it's not B. So we almost have to break it down in steps, this one, don't we? Okay, so 4 resistors of equal value are connected as shown. How will the powers to the resistors change when resistor W is removed? Okay, so the key thing we know is that when resistor W is removed, we're going to have more current, less current in the circuit. Yeah.
Oh, so all gonna.
Yeah, because this now, instead of being 5 ohms, effectively 5 ohms, it goes up to effectively being what just one single resistor is. It goes to 10 ohms. So the overall resistance in the circuit increases. You following that?
Yeah.
Good. Now, if I use this formula here, I squared R. Now the R is still the same. Now, what does it say here? Let's just look at this. The power to X will decrease and the powers to Y and Z will increase. Okay. Should we use some values? Did you use values?
Yeah.
So let's imagine
No, just
10 ohms, 10 ohms, 10 ohms, 10 ohms. Good. Let's just see it with some values. And let's imagine we have a power supply of, let's keep our values easy, 10 volts. So this here is effectively 5 ohms, and this is effectively 5 ohms, the two of them, okay? So the current in here will be 10 divided by the total resistance. So the current in this case would be 1 amp in the initial case. And the power dissipated in this would be given by I squared R. So 1 squared, yes, times R. So in this case would be 10 watts. Let's just put the power dissipated. Oops, actually, no, I'm wrong because the current splits. So we've got 0.5 amps going there because they have equal value and 0.5 amps going there. So the power dissipated in this is 0.5 squared times 10. Likewise, the same over there. What does that give me then? 0.5 squared is 0.25 times 10. So that's 2.5 watts in the current situation. Are you okay with that? In each of these resistors, 2.5, 2.5, 2.5. Are we okay with that, Tom?
Yep.
So far, so good. Excellent. Now we remove this resistor here. That's gone. W is gone. So what's the total resistance now we have in our circuit? Well, this is still 5 ohms. This is 10 ohms now. 10 plus 5 is 15. And if I use V equals IR, I can find I by saying 10, which is my V, divided by the total resistance, which is 10 plus this 5, which is 15. Yeah, we can simplify that, can't we? So 2/3 of an amp. So if now the current has decreased, we are now at 2/3 of an amp. We're in the new situation where this has been removed. Okay. So what will the power to this guy be now? So it's 2/3 squared multiplied by my value of my R, and 2 squared is what? 2/3 squared is 4/9 times 10, which is 40/9. That's the power dissipated. So what does that give us then? 40 divided by 9. So we get an actual value. We are now at 4.4 watts. So the answer is now stemming towards either C or D, because both of them have said the power in X will increase. Are you happy with that? These are wrong. We've just shown ourselves that the power in X increases, which is that resistor. You following?
Yeah.
Good. What happens here now? We've got 2/3 of an amp. Without even doing any further calculation, this 2/3 of an amp is going to split into 2. Yeah, so you're gonna have half of it, and half of 2/3 is, what's half of 2/3? You're gonna have a third going that way and a third going this way in the new situation. Before, you had 0.5. Now I squared R, if your I has gone down and your resistor is still the same, what should happen to the power dissipated in these resistors now? Down. because the I has gone down. You following?
Yeah.
So which answer would we choose?
C.
C, spot on. Good. Number 17, very difficult, not easy. This is now a question to see how well do you know Kirchhoff's laws. It's not, this is a very, very good question to put you through the paces of Kirchhoff's law. So take your time with this one.
Why does physics have to be so confusing?
I know, whenever you've got them in networks like this, but you know, you don't see a lot of them often. That is what I'll say, Tom. They're not there often. So once you've done a few of them and you've got the general experience, generally you can get some marks off them.
This is like a 1 mark question, though.
I know, which is really diabolical. In all essence, this here is effectively actually some multiple choice questions. They are 1 mark, but the time allocated for them is actually double the time you get for the other questions. So the examiner will normally factor in. So if you had a question like this here would probably be made to be 3 minutes long. And the questions, which are 1.5 minutes, yes, would they'll ensure that there's enough questions to also add that 3 minutes. So a question like this, the examiner will be giving you more than 1 minute to do.
I'll probably just leave this and guess at the end.
Leave it and guess. Well, that's the beautiful thing about multiple guess. You can guess. But let's imagine on another day that this was a long structured question and you did not have these solutions. That's what the point of this this exercise is as well. It's to try and see, you know, can you work through the problem logically, assuming you were not given the answers.
Voltage in parallel is the same. So would it be 7 across P?
Don't use that rule. Kirchhoff's laws. Now here we're talking potential difference.
Oh.
Now please note, what's Kirchhoff's first law state?
Oh, I was in for lessons. I don't know.
Okay, sum of currents, yes, into a junction is equal to sum of currents out. Correct. Okay, that's the first law. Now the second law is the one that is very hard to apply. And I say very hard because it's easily written, but very hard to understand. What does that state? Sum of PD drops in a closed loop is equal to sum of EMFs. Now, such a simple little statement, but my days, what complications and difficulties it brings. This here is as a consequence of conservation of energy, and this here is as a consequence of the conservation of charge. So in any loop, that's a loop, that's a closed loop, that's a loop. This is a loop. This is a loop. This is another loop. In all these loops, all the different loops you've seen me draw, this law applies. So it's now applying this law to answer this question. How can you apply that law to answer that question?
I'm very lost.
I know this one is a tricky one. It is a tricky one. But it's worth, now that you're doing A levels, this is absolutely key to you understanding electricity. This law, this here you do in GCSE. This is easy to apply, but not that. And this is where I want you to get the understanding of how to apply that law. Do you reckon you might be able to, well, give it a go, see what you do or what you get, okay?
I don't know how to work it out though.
There's a lot of confusion going on. Should I take some of this off? It's too many lines around here.
I wouldn't even try. I'd just purely guess.
Pure guess.
Yeah.
Okay.
Do you want to know what my guess is? See if I'm right.
Have a guess if that's what we need to do, and then I will take you through the thought process of how to think about these problems, because it's important for your A level. You know, one of these things is that once you've learned electricity, you're not going to cover it again until your second year of your exams, when you see it in your main exam. So it's better to have a solid understanding now, and then build on that solid understanding over the next course of the few months before your main A level. Okay, so have a go, have a guess if you need to, and you just use the best knowledge you've got accessible to you to try and hazard a guess.
I'll just go for C.
Which one are you going for?
C.
C, and you're spot on. Look at that.
Yeah.
Come on. You're spot on.
I don't know why it's C, but I'll take it.
You don't know why it's C, but you landed on the jackpot. Okay. So we have.
I didn't think it would be 7, and then I thought 3 was too low for P.
Oh, I see. We have.
What's it being? P being 7, 11 being 7 was like a trap set by examiner, and I thought 3 was just not right. So that's why I went for C.
Okay, good. So you actually used some. Well, calculated guessing, which is good. Calculated guessing is always better than just blindly guessing and tossing a coin.
Yeah.
Let's look at this loop here and understand Kirchhoff's laws. Second law, I mean. Let's look at the first loop. That's a loop in pink. It's a loop. It's one single path. Sum of PD drops in a closed loop is equal to sum of EMFs. This is an EMF, and it is equal to 20 volts. So here, there's going to be a drop, 7 volts. The sum of PD drops. So what should the drop be across M?
I don't know.
The sum of PD drops must equal to the sum of the EMFs. There is one EMF of 20. I've lost a PD of 7. What have I lost over M?
13.
Good. We're literally applying the law as it is. Very good. So this here is 13 volts. Excellent. That is 13 volts. So I know my answer is now down to B or C. One of these, B or C. Okay. We are now going to look at another loop. Yes. We are going to look at, which loop shall we look at? Look, they've given us a 4-volt drop here, so we can look at this loop here. Yeah. So the sum of the drops. Now, if we look at the current going in here, the current does this. It gets here and then splits. Some goes that way, some goes this way. Yeah. Let me use a different color here. When it gets to this junction, well, some goes this way and some goes that way. And it doesn't matter. We don't know where the current, maybe some goes this way, or it could be that it splits from here and goes up there. We don't know. And it doesn't matter that we don't know. But the key thing is we have to assume a direction in which the current is going to go. So if I assume that the current is going in this direction and then splits and comes down here, it means that the potential drop across this resistor, we always represent it with an arrow that is opposite to the direction that the current is going. So the PD drop in this resistor is to the left because the current I've assumed is going to the right. So this is what I call my PD drop. I have now assumed that the current goes down. So my drop is in which direction? Is in that direction. So that is 4 volts. Here, I've assumed that the current is moving in which direction? I've assumed that it's going in this direction. So my voltage drop is in this direction, because I've assumed that the current is traveling that way. You happy?
Yeah.
So the voltage drop is always in the opposite direction to the direction of the current. Now look very carefully. This 4 volts is going in the same sense as the 7 volt drop, which is pointing. They're pointing the same sense. Are you happy?
Yeah.
They're pointing the same sense. This is not pointing in the same sense as these. So when we look at this loop, this drop of 4 volts plus that drop must equal, in this loop that's purple, must equal the drop across P. These are going in the same sense. So 4 plus 7 is 11. That must equal this PD that's going in the opposite sense. So the answer, potential across P, is 11, 13. And we can also justify ourselves that this here must be 9 volts. Again, just for the sake of this exercise, let us look at this loop so you get an understanding of Kirchhoff's second law. This is the most misunderstood law by A-level students. So here now, I'm assuming that some of the current goes this way. So my PD drop is over like so. Okay, and my PD drop there is 4 volts. Here, I'm assuming that current carries on because it comes down here and then it goes there. So my PD drop here is in this sense. Now, can you say that this PD drop and that PD drop, these arrows are pointing in the same sense? This gray arrow and that 4 volts drop.
I've noticed a bit of a pattern.
Can you see that?
Yeah, if you take the biggest value and you subtract it by all the other voltages, you get 0 in both loops.
Yeah, so if I say now here, this voltage here plus that voltage must equal this voltage in this loop in black.
Yeah. It's the same for the other side as well. That's what I saw.
Yeah, absolutely, Tom. So you're absolutely spot on. So what do I know here? I know that the PD across M is 13 volts. Okay. So I know that 4 plus this, because they're going in the same direction, must equal 13. So this must be 9. Did you follow that?
Yeah.
Now, if you've not yet learned this rule, I cannot overemphasize how important it is that you're able to apply it. Otherwise, you will have a huge gap in your knowledge of electricity at A level. So it's important to be able to do what I just did. And in previous, when I was doing my A levels, we used to have circuits where you had cells of all sorts connected in different polarities, 6 volts, 9 volts, different polarity, you know, a positive connected to a negative, and you had loads of them, very complex networks. And the only way my life was made easy is because I knew what this meant. So it's worth your while making sure that you go through this in your own time again to make sure you understand what we've just done. Is that okay? You can watch the video anyway, and you can rewind it back to hear what I've just said in case you've missed a point. Okay. Righty, we're doing good, Tom. Number 18.
I feel like it's C or D.
Not quite.
Okay, it's A or B then.
Yes.
Is it A because R is parallel to the voltmeter?
That's not the reason why, but it is A.
Oh.
Okay, it is absolutely A, but it's not the reason why. Now, voltmeters, ideal voltmeters. What do we know about an ideal voltmeter in terms of its resistance? You need to know this. It's absolutely key.
Well, it has a resistance of some sort, but every electrical component does.
But look at the word. I've said an ideal. So the perfect voltmeter, what resistance does it have?
A greater resistance than the resistor in the circuit.
Not quite. But remember this, commit it to your memory bank. Ideal voltmeter has infinite resistance. That is why when we are finding the EMF of a cell and we connect a cell with an internal resistor and you connect a voltmeter across it, this voltmeter will only give you the value of the EMF because there is no current passing through. I equals to 0 because the resistance of this is infinite ohms. When you've got infinite resistance, no current can pass through. And if we use our equation, V equals E minus IR, this value disappears because current is 0. So V equals E. So an ideal voltmeter has infinite resistance. Are you following so far?
Yeah.
Good. An ideal ammeter. What's the resistance of an ideal ammeter? Remember, it's placed in series. Ideal ammeter.
It's much less than that of the.
Yeah, so what would you say?
It's low.
Has 0 resistance. And the examiner will test you on this knowledge. So I strongly urge you to commit this to your memory bank. So an ideal ammeter has 0 resistance because you don't want it impeding the flow of what you're trying to read, what you're trying to measure. So this has to have 0 resistance. So which condition is necessary for an accurate value for R to be obtained? R is much smaller than RV because this we're assuming is infinite. R doesn't have to be much smaller than RA. This has to be 0 anyway. Okay, so the right option is A. Okay, good. Here's a very good one. Very, very good question. I will try and enlarge this so you can read the graph good.
You zoom out a bit. I can't
Yeah,
read the
yeah,
top
yeah,
question.
yeah. I'll just bring, there we go.
You just scroll to the top of the graph, please. I wrote down those answers.
Yeah, I'll just bring.
Is it 1.5 kilo ohms for the thermistor value at 730? Because I can't exactly read it from here.
Sorry, is
on
it?
the graph. At 730, what is the ohms on the graph? Because I can't really read it very well.
Okay, sorry. I shall do justice, and there we go.
It says just assume it's 1.5.
So which one are you going for as the answer?
I've not answered yet. I'm just thinking.
Oh, okay. Oh, all right. So have you managed to read the value?
Yeah, I think it's 1.5, roughly.
I'll be very careful when you
Like
read
1.4.
it. Make sure that you
Can't really read it very well.
So it's saying, why is this stuck? At 0730, an output of 6 volts is required. What value of variable resistor? 0730. Oops. Oh, come on. Oh, I'm just gonna have to use the mouse. 0730. Yeah, so it's halfway. There we go. Okay, and we are going. Is that right? Round about there anyway, give or take.
Yeah, so that's 1.4.
Please note, what does that say?
Kilo ohms.
Correct.
Mm. I feel like it's 1.5.
You get 1.5 for that one.
Yeah, I think I'm wrong.
Okay, let's look at it together, because this is definitely one worth learning from, because these form the type of staple type of questions you can get. So it's worth knowing how to go around problems like this. So let's just read this, okay? The thermistor is connected to the potential divider circuit. Where is the thermistor? There it is, okay? What voltage do we have? We've got 9 volts. There's 1.5 kilo ohms there. This is a variable resistor. That's a fixed resistor of 1.5 kilo ohms. And the output is being taken across these two resistors, meaning the variable resistor and the fixed resistor. So it says at 7:30, we want 6 volts here, meaning that we are going to have, by Kirchhoff's second law, in this loop, the sum of PD drops must equal to the EMF. The EMF is 9 volts. Yes, so if there's 6 volts here, across here, I must have 3 volts.
Yeah, I had that.
Good, okay. Now it says an output of 6 volts is required, and it's at 7:30. And at 7:30, we know that this guy here has 1.4 kilo ohms worth of
Ah, right. I
this,
know I went wrong.
because we
I did
need,
the other way around.
sorry?
I know I went wrong.
Okay, do you want to have another go at it?
Yeah, if you in like
Yeah,
20 seconds.
go for it.
Okay.
One second, Tom, I'll be with you shortly, yeah? Just need to get something from the door quickly.
Oh, never mind.
Tom, sorry, I was just picking up a parcel for the neighbor. Do apologize. How are we doing? Have you managed to suss an answer?
Got 1.5 again.
Which one did you go for?
I did it. I thought the one which was like RT or whatever next to it was the thermistor. And then I just got 1.5 again. So
oh, you got the mixed around. Okay, very good. 4.5. You could have used the number of roots, V1 over R1, because I always said when you have a potential divider, these equations should ring to mind. So this here now can be treated as one resistor. 1.5 plus 1.4 is 2.9, and there is 3 volts across it because they're in series. That's why we can add them. So now we have 3 over 2.9 kilo ohms. Now I don't need to put kilo ohms because this stuff is also in kilo ohms, so that's fine. Yeah, and this is V2, which is 6 over the total resistance that these two will form. So 3 over whatever that total resistance will be, and they're in series. So if I know one of them, I can take away that value from this value of the resistance I get. Are we happy with that? So we can get, say, R2 is equal to 6 times 2.9 divided by 3. And what does that give us? If I punch that, 6 times 2.9 divided by 3 is equal to 5.8. Now 5.8 minus 1.5, I get 4.3, but the closest one, it's all to do with how you read the graph really. So this would be the closest one. Alternatively, you could find what the current is in the circuit. So you could use this part of the circuit here and say, well, the current that will be passing in these 2 resistors is the same as the current passing in these 2 resistors here. So you can say, well, what's the current passing in those 2 resistors? You need to choose the total potential difference across those 2. So you'd say 3 divided by 2.9 times 10 to the 3. That's the current in that branch. So if I know what the current is now, I know that I times R, which is V, or across this resistor, yeah, added to the potential difference across this resistor, which is also given by I times R. So I take this value here of my current, I multiply it by the value of my resistance here, and I know that the total must equal 6 volts. So if I take this here, so 3 over 2.9 times 10 to the 3 multiplied, because that's my current I, multiplied by R, which is 1.5 times 10 to the 3, gives me the voltage across this resistor. And then all I simply need to do is do 6 volts minus this value of potential difference. And then I should divide the value of the current, which I've got here. So I then divide this by 3 over 2.9 times 10 to the 3. This again will give me the value of that resistor here. Did you follow that?
yeah.
Good man. So there's always more than one way of skinning this rat, cat, whatever you want to call it. And it's always worthwhile knowing the 2 methods. Right, last one on this series, and then we start looking at the photoelectric effect. Okay, so this again is now a test, but this time it's a test on Kirchhoff's first law, not Kirchhoff's second law. Okay? Well, maybe a little bit. I've not done the question fully myself, but I think looking at this, there's going to be elements mostly of Kirchhoff's first law, but you might have to use Kirchhoff's second law as well. So just have your wits about you.
And it's just gonna be another guessing one.
Another one for the lottery.
I have to decide what I think is the best guess.
Make sure it's a calculated guess.
I think either B or D. It's not my answer, but B or D are looking promising to me so far.
B or D, you're absolutely right, Tom. It's either B or D. Now you've got to whittle it down.
I'm going to write it out.
Finally, multiple choice questions, Tom. It's about finding one right. Which of these is the right thing, and where is it? Is it in B or is it in D?
It's the 1.4 and the 0.4, which made me think B or D. Does it tell us what the total current is in the thingy?
Not quite. No, it doesn't. Tells you what the reading on ammeter A1 is, but that's not the total current. Because by the time now just help yourself out, make your life easy. Yeah, that's the current moving from the positive terminal. Some of it goes that way, some of it goes that way. Okay, it gets to that junction. Some of it proceeds this way, some of it proceeds that way. Okay, and they all come back like so and meet up at this junction back into the cell. So I've put a few arrows there, and remember what Kirchhoff's first law says. Sum of the currents into a junction. Where are the junctions here? That's a junction, that's a junction, that's a junction, that's a junction. Sum of the currents into a junction is equal to sum of the currents out of the junction. So try and apply that law.
It's got to be a guess. I don't know the difference. So,
that's okay. We'll look at it together. That's okay. Which are you guessing?
I had 3 different junctions / routes written out. I had loop 1, which was A1 and A2.
Okay.
Loop 2, which was A2 and A3, and then loop 3, which was A3 and A4.
That's fine.
But I'm gonna guess. I'm gonna guess B.
You're gonna guess B?
Yeah.
Unfortunately, this time around, the guess didn't land on the right letter. But let's look at it logically to see how is it you go around solving these problems. A1 is 0.6 amps, you are told, or we are told. So 0.6. Now, we don't know what these values are. A2, A3, and A4. Okay, what are we told? All the resistors are identical. We have got a choice of either using letters or using numbers? I mean, I can call these R, or I can put some numbers. What do you prefer? I will work with whatever you prefer.
Some numbers, please.
Super. You love numbers. That's okay. So let's call this 1 ohm, 1 ohm, some simple numbers, isn't it? Nice and easy. There we go. So if I look at this loop here, let's use a different color. If I look at this loop here, the sum of potential difference drops must equal the EMF. The sum of potential difference drops. I have said my current is going in that direction with the arrow. Yes. So my potential difference drop will be in which direction, Tom? That direction and that direction. Potential difference drops only happen across resistors or components that have a resistance. And we show that drop in an opposite direction to the direction that the current is moving in them. So we apply Kirchhoff's second law. So here I'm going to have 0.6 volts. I've simply used V equals I times R. Current is 0.6. My resistance is 1. Here I'm also going to have 0.6 volts potential drop. So the total drop in potential is 1.2. This must equal my supply, my EMF. Are we following so far? Good. So I've got 1.2 volts in this case here. And the thing to note now here is this idea of potentials. I didn't say potential difference, I said potential. So if this is at a potential of 1.2 plus 1.2, this negative terminal will be at a potential of 0 volts. We always take the negative terminal to being at 0 volts. And that's what creates a potential difference of 1.2 volts, because there's plus 1.2, take away 0, we have 1.2 volts. So these are conductors, so we assume that there is no drop in potential. So if this is at 0 volts here, this is also at 0 volts. If this is at 1.2, everything on this conductor will be at 1.2. So this here is also at 1.2 volts. That's the potential at this green dot. And everything on that rail, everything on this rail, before we meet a resistor, as long as it's a wire, everything will be at 1.2 volts potential on this wire until we go past the resistor. So this here is also at 1.2 volts. Are you following so far? Everything here is at 1.2 volts. Everything here, 0, 0, until we meet a resistor. So we don't know what the potential is there. Neither do we know what the potential is there, but that's okay. For now, we're breaking the problem down. So I have 1.2 volts and I have 0 volts here. So what is the potential difference across this resistor here? It's 1.2 take away 0. Yeah. So the potential difference across this resistor is 1.2 volts. So what current must be going through it if it is 1 ohm and there's a potential difference of 1.2 volts? Well, I is V over R. So the current through there must be 1.2 divided by 1. That is going to be 1.2 amps. Are we following this so far?
Yeah.
This is a very, very, very challenging question in certain senses, but there's a lot you learn from it. And the whole key thing here is I want you to get exposure so you learn that there's lots of ways of looking at these things. Okay, so there we go, 1.2. This is at 0. Now I know that's at 1.2 volts. I labeled it because it's on the same line, same conductor. And this is at 0 volts. So between these 2 points here, I have got a potential difference of 1.2, and I have 3 resistors. Now I could have either used Kirchhoff's law and looked at this loop, or I can simply just look and say, what is the potential difference between these 3 resistors? Well, it's 1.2 volts, and I've got 3 of them. So what current must be passing through? What are they going to do? They're going to share this potential difference equally. So I'm going to have here 0.4 ohms, sorry, volts, beg your pardon, 0.4 volts here and 0.4 volts here. If I know what the voltage is, I know what the resistance is, and these are in series, I can work out what the current in one resistor is, because it will be the same as the current in this resistor. There's no branches or loops for the current to branch out. So to get the current in this loop, I say 0.4 divided by 1, which gives me 0.4 amps, which must be the same current coming through here. So this I get as 0.4, that I get as 1.2, and A2, well, it's now just a case of applying Kirchhoff's first law. If there is 1.2 amps this way, is it? Hang on, I better be careful here. We've got 1.2 coming in here, and then 0.4, so it means the total coming in here will be 1.2 amps plus 0.4 amps. They meet here, so I'm going to have 1.6 amps coming in through there. But then it meets 0.6 amps, which is coming from this direction, and they end up proceeding going upwards. So 1.6 plus 0.6 gives me 2.2. So that's the total passing through there. So this should be 2.2 amps, which gives me the right answer as D.
Yeah.
Did you follow that?
Not a fun question.
Sorry? No, not a fun question. I agree with you. But there was a lot to apply there. And that's the sort of level that you want to get to be able to make those, if you like, links while you're analyzing a complex circuit like this. Hopefully you don't see something as diabolical as this, but if you do, just have your wits about you, label what you've got, remember your principles on Kirchhoff's laws, and remember your principle on potential as well. Not just potential difference, but the element of potential. And I know you have an understanding of potential, because the second question you did today was evaluating potential difference between 2 different places in a circuit, and you worked that fine. So there is a general understanding, it just needs to be refined. Okay, good. Tom, did you want to take a quick 2-minute breather, use the toilet, have a glass of water or something before we move on into the photoelectric effect?
I'm ready to carry on.
Okay, you're happy to go straight into it. No problem. Okay, so blank page after current. Right here. So we are going to be trying to demystify this business of the photoelectric effect. Matter of fact, what might make life a little bit easy is we're going to try and do a bit of a concept map. So everything is on one page and you can see the links. I suppose that's probably an easier way to look at things. Okay, so the photoelectric effect. Well, what's the main, what ideas are the key ideas that we explore in the photoelectric effect? Firstly, the key idea is this idea of the fact that light behaves as a particle, or light behaves as particles. So light behaves as particles. And we say that these particles come as discrete energy packets. And the name we use for that is we call them photons. Now, these photons possess energy, and the energy that a photon, a single packet of light, possesses is linked to the equation E equals hf. In words, we're saying the energy of a single photon is equal to Planck's constant, which is h, multiplied by the frequency of that particular light. Now, I say here light, I should really refine my phrasing and say that electromagnetic radiation, electromagnetic. Okay, yeah. So it's not just light, but really when you talk about the EM spectrum, everything in the EM spectrum, if you remember, we've got radio waves, microwaves, infrared, all that forms the electromagnetic spectrum, and all the elements of that spectrum behave as particles. But they also behave as waves, but we're not going to delve into that so much. We want to understand this essence of the photoelectric effect. So E is equal to hf, but also because we know that there is a relationship that C equals f lambda, therefore, sometimes we express this formula as hc over lambda. I've just rearranged C over lambda for f and whacked it in place of f. So this is another key formula we need when we are finding out the energy that a photon possesses. Now, the key idea here in the photoelectric effect is that a photon which possesses the right amount of energy, yes, can interact with an electron, a surface electron, or an electron on the surface of a metal. And this can give it sufficient energy to then escape the electrostatic force of attraction from the positive ions within the bulk of the metal. Now, remember, metals exhibit what is known as metallic bonding. So if I have positive ions in the bulk of my metal, and these positive ions are in a fixed lattice, so regular arrangement right throughout, we also have delocalized electrons or valency electrons. These are essentially electrons from the outer shell, which are mobile and therefore do not belong to any one particular atom. So we call them delocalized electrons. So if I have a photon, okay, that's my photon with that symbol there. This can interact with the surface electron. Now note, of course, that there is an attraction between positive and negative here. So these electrons are actually bound by that attraction. However, they can get sufficient energy, which can allow them to escape. And the interaction that a photon has with an electron is known as a one-to-one interaction. Now that's a key word, key phrasing you need to use when describing the photoelectric effect. You need to remember this sentence, one-to-one interaction, meaning one photon can only interact with one electron. Are we clear on that? So this is a key phrase. You want to quote this any chance you get. Good. So if we look at it from an energy balance point of view, the energy that a photon, because remember, we said that the photon needs to have a certain minimum energy. All right. So if we just expand this, we're going, oops, come on. If we expand this to say, we're just going to say photon interacts with surface electrons on a one-to-one interaction. Okay, now the necessary condition is that the photon must have energy greater than the work function. Now, what do we mean by this term, the work function? So for dislodgement to take place, the photon must have energy greater than the work function for emission to occur. Sorry, I should have said for emission to occur. So what is this work function?
Is it the minimum amount of energy for a photon to liberate an electron from the surface of the metal?
You're absolutely right. And we can find that out that can be found out using the formula. So we're going to say the work function is given the symbol phi. And this is given by multiplying Planck's constant with something known as the threshold frequency, which I've labeled as F naught. So this here, F naught, is equal to the threshold frequency. So the frequency at which emission just begins. So the threshold frequency times by Planck's constant gives us the work function, okay? Again, this can be rearranged to hc over lambda. So here, the minimum frequency, please note that frequency is inversely proportional to wavelength. Note that. So if this is the minimum frequency, it can also be represented as the maximum wavelength. Maximum wavelength gives me minimum frequency. So the threshold frequency is the minimum frequency at which emission occurs, but you can also think about it in terms of saying that this is the same as phi equals to hc over lambda max, where that's the maximum wavelength needed to lead to emission of electrons. So it's worth knowing that this is a minimum frequency, but it can be arranged to a maximum. In other words, a question could say, what is the maximum wavelength at which emission will occur? You could be asked that. Or what is the minimum frequency? Note that if they're referring to maximum, it's simply the same as the minimum or the threshold frequency. Are you following so far?
Yeah.
Good. So photon comes in and this guy has got energy equal to HF, where HF is greater than HF naught. F naught is the threshold frequency. So there we go. It now interacts on a one-to-one basis. So if the energy of the photon is greater than the work function, what's going to happen to the excess energy? So imagine the threshold or the work function is 5 electron volts and the photon comes in with 10 electron volts. What's going to happen? So this is equal to 5. What's going to happen to the excess 5 electron volts of energy left?
I'm not sure.
Okay, not to worry. Well, in this case, remember, one of the big ideas in physics is this conservation of energy. If ever there are going to be 3 laws you need to know in physics, it's conservation of energy, conservation of momentum, and conservation of charge. These are key ideas that underpin the functioning or how physics operates. So think to conservation of energy. If this has got 10 electron volts, or let's just say 10 joules, and this only needs 5 joules to be liberated, the other 5 joules of energy is going to go into giving it kinetic energy because it's going to move. So we can therefore say that the energy of the photon is shared. Some goes towards getting the electron dislodged due to the work function, and some of it goes into providing kinetic energy. And we say that this is EK max. Why? Because the surface electrons will have maximum kinetic energy. Much harder for the ones inside the bulk of the metal because they are attracted by more forces. So it's much, much harder for them to, they won't escape with a maximum kinetic energy. The fastest moving electrons will be from the surface. They are the least bound, so to speak. Okay, so this formula, if ever you were to quote this formula, please, please, please do not just say HF equals 5 plus EK, which is kinetic energy. You have to say max. That has to be there. So this here is max kinetic energy. And this here is the work function. And this here is the energy of the photon. This here is max kinetic energy of the electron, please note. So here we go. Energy of the photon goes towards dislodging it, but also providing it with some kinetic energy. That is in simple terms. Are you following that so far?
Yeah.
Excellent. Right. So with that said, and we understand this formula, we now also need to understand this idea of intensity. Photoelectric effect is also linked to intensity. Now, what is intensity?
It's the amount of particles of light.
Not quite.
No.
Not quite. So I want you to commit this to your memory bank, write it down in your set of notes, note to self. It's important because it underpins how well you're going to understand this. Intensity is power in physics divided by area. And if you can't remember that formula, at least please remember the units of intensity. And the units of intensity are watts per meter square, because power is in watts, area is in meters square. So if at least you can remember the units, this hopefully should allow you to remember the formula, because you can see that you've got a quantity in power, which is watts, and you've got a quantity in area, which is in meters square, and they've been divided by one another. That's why you've got a -2. Okay, so this idea of intensity, how does this link to the photoelectric effect? Well, when you're illuminating a metal surface and you are sending in these photons, they have a certain amount of energy. So you will be transferring a certain amount of energy every second. And that is what power is. It's how much energy are you transferring every second, divided by the area over which you're transferring that energy every second. You get this quantity known as intensity. And of course, the intensity has a play into what happens to the electrons that are emitted, or if you like, dislodged from the surface. How is this all linked up? Well, power, if I know the number of photons I'm sending out a second, and I know the energy of each photon, surely I can multiply the number of photons per second. We're running low on space. Number of photons per second. Let's call that N. And I multiply that by the energy of each photon. And we know the energy of a photon is E equals HF. So that's energy of a single photon. And I divide that by the area, I get a value for intensity. Okay, so this is the formula for intensity. Now let's just think a little bit about how does intensity affect the electrons that are emitted? How does it affect them in terms of the kinetic energy, so on and so forth? So if I am already emitting, or rather the photoelectric effect is at play and electrons are leaving a metal surface, and I increase the intensity, meaning I increase the number of photons per second, how does that change the maximum kinetic energy of the emitted electrons? How would that change it? Would it change it in any way?
No.
Go on then, tell me, explain your rationale to me. So why would it not change the maximum kinetic energy?
Because it's a max, you can't get greater than that.
Not quite. Okay. Now, again, the question I just posed there forms a staple, as in examiners like asking that. So you want to really know how to get full marks on that one. So you are going to state in explaining it, because it is a one-to-one interaction, increasing the number of photons per second simply increases the number of interactions. So there will be more electrons emitted. Now, these emitted electrons, actually, we call them photoelectrons to distinguish them from the other electrons. So we call them photoelectrons. So because it's a one-to-one interaction, yes, and we have increased the number of photons reaching the surface a second, this will lead to more photoelectrons being emitted per second. However, because the energy of the photon is still the same, HF, and the work function is still the same, EK max remains unchanged. Are you following that?
Yeah.
Very good. So have a go at explaining it to me then. How would you say it?
What the frequency?
So why, yes. So why does intensity not affect the maximum kinetic energy? Why does increasing the intensity?
Increasing the intensity only increases the amount of photons. As it's a one-to-one interaction, the amount of interaction occurs, the amount of interactions that occur increases.
Very good.
Meaning more photoelectrons are released or liberated, whatever
Good.
the correct terminology is.
Good. And because the energy of the photon, of a single photon, remains unchanged, the EK max remains unchanged as the work function is still constant. Are you following that? Very good, Tom. Well done on that one. Okay, so you need to be able to articulate yourself like that, because this could have easily been a 4-mark question, the one I just asked you. So there are a lot of linkages you need to make. Okay, good, well and fair enough. But of course here, Tom, you must be, I'm hoping you can see that to increase the intensity, you can either increase the number of photons, or what else can you increase?
The surface area of the metal.
Yeah, but if you increase the surface area, you're going to decrease the intensity, but we want to increase the intensity. So, okay, we can play around with the area. What else can we play around with? You're right, we can play around with the area. What else can we play around with?
Frequency.
Play with the what, sorry?
Frequency.
Correct. Absolutely correct. So now imagine I increase the intensity by increasing the frequency. So my number of photons are still the same, but I've increased the frequency. How will this affect the photoelectron that is released? Now try and explain that. Now make linkages to the formula, to everything we've spoken about, one-to-one interaction, and try and see if you can explain it. So I've now increased intensity by increasing the frequency. My N is still the same. as is my A.
What am I trying to find out? Yeah.
We're trying to say what will happen to the photoelectron released when we increase the frequency, but keep the number of photons reaching that surface area a second the same.
As the frequency increases, the number of photons remains the same, but the intensity increases as a result.
Good.
The intensity of the photoelectrons is increased.
Any thoughts on that one, Tom?
Yeah, I shared them like 2 minutes ago. All I can think of.
Oh, sorry. I thought you were still, sorry. I'm very, very sorry for that. Okay. Right. So again, to explain that one, throw in that phrase, any chance you get it. Yeah. Because it's a one-to-one interaction, the number of photoelectrons emitted per second will remain unchanged. In other words, we can also refer to this as if this was in a photocell. So in a photocell, this would be connected to the positive, and then you would illuminate. That's your beam there, or flashlight if you like. You would illuminate this surface of this metal, and it would send off electrons, and these electrons, of course, would go streaming towards the oppositely charged end, the anode in that case, or sometimes known as the collector. Okay, so if I just where are we going to make this? There we go. Okay, so because it is a one-to-one interaction, and if you had an ammeter here, your ammeter would be measuring what we term as your photocurrent. Okay, so it's a one-to-one interaction, so the number of photoelectrons emitted per second remains the same. However, because the frequency has increased, the energy of the photon is now gone up. The work function is the same. So what should happen to the maximum kinetic energy of the photoelectrons?
Would it also go up?
It has to. Energy conservation has to. So the maximum kinetic energy of the photoelectrons goes up. Now, did you see that linkage of ideas?
I had it written down, but I thought I was meant to talk about intensity.
Yeah, but you're still talking about the intensity. So intensity has increased because frequency has increased. But because the number of photons per second are the same, and it's a one-to-one interaction, the number of electrons emitted per second will still be the same. However, the energy of the photon has now increased, and by energy balance, the EK max must therefore go up as the work function is constant. Does that make sense?
Yeah.
Excellent. Right. Now, we're going to touch on this idea, or even before we go on to that, let's move on to mapping this equation HF equals to the work function plus EK. What have I forgotten there?
Max.
Thank you.
Can we
So
do
we're going
that?
to think of trying to map this onto y equals mx plus c. So if I had a graph here where I had EK max and I had frequency, what would my graph look like?
I feel like the gradient would be something to do with Planck's constant, because Planck's constant is the only thing that's multiplied in that equation.
Yeah.
Would plus C be the work function?
Nearly there, nearly there. So the first thing you've got to do is you've got to rearrange it. On the y-axis, I've got EK max. Yes. On the x-axis, I've got something related to frequency. So frequency in my formula is here. So this here will take up the place of my HF. Yeah, well, sorry, my HF will take up the place of my MX, sorry. My HF will take up the place of my MX because the F corresponds to the X. But of course, now I can see that, hang on, there's a rearrangement of this equation taking place because now EK max is the subject. It's the Y. So in this case, I need to rearrange this EK max and make it EK max equals 2. So what would I have to do? Well, I'd have to take this to the other side and it would become minus phi upon crossing the equal to sign. So this then now becomes EK max equals to my MX is HF plus C, which is the minus phi. So if I map everything, there we go. That's my X.
So I said the work function would be plus C.
Yeah, but it's not quite. This is where I was being very, very pedantic here, but I need to be because we're doing physics, so I need to be super pedantic. The C is minus phi.
Yeah, okay.
So this graph, because it's minus phi, there you go, that's my minus phi. Not positive, minus phi. And it will do something like that. What will the gradient now represent?
E Planck's constant.
Correct, very good, excellent. And what does this intercept here? Yeah, what does this intercept represent?
Is that the threshold frequency?
Very good, Tom, very good, very good. And so if I was given a graph like this and I needed to work out the work function, I can either multiply this value by h, or I can use that intercept. It all depends what I'm given. If the graph only starts from here, then I simply take that value multiplied by h. But if the graph extends all the way to the intercept, then I simply take the positive value of my negative intercept. Are you okay with that?
Yeah.
So if I took another metal with a higher work function, what would this look like? Well, it would still be the same. The slopes have to be the same because in each case, m equals to h. So the slopes have to be identical. Are you following so far?
Yeah.
Excellent. Right. Now, the next thing we're going to look at is this idea of stopping potential. Now, if I have a photo cell, as in before, there we go. I've got my collector here, and I've got my emitter. And this is my collector. And my collector would have to be positively charged. And this is negative. And I irradiate it with EM radiation that's got energy greater than the work function. Okay. And we have this circuit like so. And I have a variable power supply. And I'll indicate that with an arrow, say it's a variable. Now, when emission starts, I can make this here slightly, because it's a variable power supply, I can change this polarity to be ever so slightly positive and keep changing it, yes, until I get to a point where no electrons are being emitted. At that voltage V, where the photo electron emission just stops, that is what I call my stopping potential. Okay? Now, the stopping potential, if that occurred at a potential, say Vs, I can work out what the energy of the electrons must have been for the fact that they're now just failing to reach the collector. So once I measure V on my voltmeter, I can equate that to the energy that the electrons or the photoelectrons possess. How am I going to do that? I use the formula V, or potential difference, is equal to energy transferred divided by charge, Q. So to work out the energy that the electrons would have, which is just preventing them from reaching the other end, if I multiply this V by Q, I get E. So if I multiply, well, the charge of an electron would be E. E times Vs would give me what we would now call here, this would represent the maximum kinetic energy of the surface electrons. And Vs here represents my stopping voltage or potential. And this idea of multiplying potential difference by charge to equate to energy becomes relevant in this topic because you will see the unit of the electron volt. And the electron volt really generates from here. So if I have one electron, or if I have 1 volt, and the charge is simply 1 electron, the charge of 1 electron, this is the same as 1 electron volt in energy. And we can see that it is an energy unit because potential difference multiplied by charge gives you energy. So this here is in joules, please note. So this is another unit of energy. So 1 electron volt is equivalent to 1 multiplied by the charge of an electron. It's equivalent to 1.6 times 10 to the minus 19 joules. Now it's useful, it's very, very useful, again, to simply note here that if we know what the stopping potential is, say it is 8 volts, then we know that the energy of the electrons will simply be 8 electron volts. That's why we use the electron volt as a unit. Much easier. Instead of us quoting this number in joules, we simply take the value of the voltage at which emission stops and we put an E to it. And we know that 8 electron volts is the energy that is the energy that the electrons possess, or the maximum KE. And to convert this into joules, you simply multiply it by 1.6 times 10 to the minus 19. And this will be in joules. Okay? You following that okay?
Yeah.
Super duper. And I think, Tom, that is pretty much all there is to talk about when it comes to photoelectric emission. Shall we have a go at some questions then?
Okay, can we do de Broglie wavelength for 5 minutes, please?
Sorry?
Can we do the de Broglie wavelength for just like
Oh,
5
yeah,
minutes?
certainly. If you want to do that instead of going through questions, that's absolutely fine. I can send you the questions after. Yeah, no problem. Okay, so after current. Cool. Now, this idea, this really is looking at what we call wave particle duality.
Yeah.
And here, the equation we say is that lambda is equal to, or in other words, h over the momentum. Now we can see already here that particles and waves are being brought together. This represents the wave side. And we know that only particles possess momentum. So this here represents the particle side. So it's one equation that's brought a wave and particles together. So if we know what the momentum of an object is, we can work out what its wavelength is. And this wavelength is known as a de Broglie wavelength. Now, de Broglie's theory simply states that depending on the circumstances, well, I suppose in other words, we say matter displays both particle and wave-like behavior. A classic example is where you have a cathode ray gun. They love this one. So there's thermionic emission, and you essentially have electrons accelerated to a positive potential. So you have some positive plate, some negative plate. And these electrons are essentially boiled off via thermionic emission. So this is not the photoelectric effect. Now we are releasing electrons via heating. So electrons can be released from a metal surface via heating or via illumination with light as well. Anyway, aside from that, these electrons are then accelerated through this potential difference, because of course that's positive. And you have at the end here a zinc sulfide screen. Oops. So you have a zinc sulfide screen. Now this is a fluorescent material. So when the electrons, and by the way, they are passed through a thin piece of graphite. I should have mentioned that. Graphite. When they pass through the thin piece of graphite and they hit the zinc sulfide fluoresces, or it scintillates. And what you notice, if you had to look at this end on, so if you had your eyes end on, what you notice is, you notice on that screen, you notice a series of rings. Now these rings denote a diffraction pattern. And you can only get a diffraction pattern from waves. So the electrons were accelerated in an electric field. They were behaving as particles at this point. Particle behavior. Because only a particle can be accelerated. However, when they hit the screen, they form a diffraction pattern, and at this end, they are displaying wave-like behavior. Okay, so it's very important to note that this here, the cathode ray gun, is a good demonstration. And sometimes I've seen 6-mark questions asking you to explain how wave-particle duality is represented or is demonstrated by this cathode ray gun, okay? So just note that. I'm not going to go into all the nuances of what happens when you increase the voltage and how the pattern changes. Don't worry too much about that for now, okay? I can always go into more of those nuances in more time. The other thing to note about this equation, however, is that we can also represent it differently, because we can see that this mv, which is the momentum term, momentum, can also, or is related very closely to the kinetic energy formula, half mv squared, mass times velocity squared. They're kind of similar. So we can play around with this kinetic energy term, and we can represent this formula in terms of kinetic energy. Do you want to have a try and go at that, or do you want me to go straight into it and show you how to do it?
No, it makes sense now because I was using the wrong equations for a practice question. I didn't realize I could use that one. So
Yeah,
now I know how to solve that question now.
excellent, excellent.
Yeah.
So if I manipulate this, I get that 2ek equals mv squared. But hang on, I'm nearly there. But I want mv, I don't want mv squared. So what could I do? I could do a bit of a maths trick, times both sides by m, because that still means the equation is unchanged. I've times by the same thing. So that's mathematically okay. So now I get 2mek equals m squared v squared. I'm getting there. And how can I get there? I'm going to square root this guy. Because if I square root m squared v squared, the square root of that is mv. And because I've square rooted this side, I need to square root the other side.
Substitute that in for momentum.
Absolutely, spot on, Tom. So I've got another useful equation, which is h over root 2m multiplied by ek. This is a very, very important form, and the examiner loves having a field day with this. So you need to be confident with applying it. So let me just give you a scenario. Let's imagine that the kinetic energy, if Ek changes by a factor of 2. So imagine an object now doubles its kinetic energy. By what factor will its de Broglie wavelength change? By what factor does lambda change? Now, again, you can use numbers if you wish, but I'd like you to have a go at it.
I substituted some numbers in.
Yep.
I had h equals 4, m equals 4, ek equals 4. I got 2, root 2 over 2. And I had h equals 4, m equals 4, ek equals 8. And I got a half.
So by what factor does lambda change?
Root 2.
Root 2?
Yeah.
Or do you mean 1 over root 2?
I don't know. Actually, no, it's -1 plus root 2 over 2.
Okay. I will just use letters. It's a bit of a skill as well for you to see demonstrated. So root 2m. Now the ek, I want to work out what my new lambda would be. My ek, however, is twice the original value. Sorry, 2ek. So what do I see here now? I can see that I can take out this 2 from here, but I have to take it out as a root 2. And then I still have the same thing, 2m ek. Now this looks like the original. This is the original lambda here. It's hidden. This is the original lambda. So my new lambda, lambda new, will be equal to the original lambda divided by this root 2 term. So it changes by a factor of 1 over root 2. Did you follow that?
Yeah.
Good. Excelente. Right then, Tom, we have definitely come to the end, and I think it's a good place where we've stopped at. Well done today. I'm going to send you some extra practice questions. Do you have any other questions?
No, I don't. But thank you.
Is it making a lot more sense to you now?
Yes, slowly but surely I'm getting better and better.
I'm glad. I'm so glad about that. I'm so glad to hear that. Excellent. Well, good luck tomorrow. Definitely, just have a little strategy on the multiple choice. Try and do the easier parts, the more kind of like wordy type ones, get them out of the way. And then that will hopefully leave you with some time to do the calculation of parts easier. You have a little bit more time, but make sure make sure you pace yourself. Okay, make sure you pace yourself more than anything. Yeah, good stuff, and all the best tomorrow. All the best tomorrow. Okay, I hope it all goes well. Yeah,
Thank you.
good stuff. So I shall see you. When did you want the next lesson then?
I'm not sure since it's after exams.
I know. I know. Okay.
It might be September time or something for books and stuff like that.
Yeah, that's absolutely fine. Because I still owe you how many lessons? Just trying to think here. 4 plus 2, 6, 9. I owe you 3 lessons anyway. So if ever you want to, because I know we'll be learning new topics. If you want to go through some of the stuff learning at school just to stay on top of things, or you want to go a step ahead and start learning a bit of what you might do next year as well, that way, you've already seen it, and you'll be getting a step ahead. I always advise that if you can, it really helps, because the sooner you finish the A-level course, the syllabus, the better. Because what really makes you, an A-star, an A-grade student is the amount of practice. And so the sooner you can finish it, the more time you're going to have to practice, and you're going to have exposure to so many questions. You'll be going into that exam very confident, knowing that you've seen a lot of questions. Yeah. So think about that as a strategy, as opposed to just kind of trying to move in tandem and keeping pace with the lesson. I definitely advise that if you wish to do so, I'll more than happily use the remaining lessons to get you a step ahead if you wish to. Okay.
Okay.
Super. Right. Have a lovely, lovely, lovely rest of the day, Tom. And good. Go and enjoy the exam tomorrow as well. All right.
I'll try. Thank you.
Lovely again. See you soon, and I'll send you the notes.
Bye.
Cheers.
Thank you.
Bye now. You're welcome. Bye-bye.